1934, a physicist told a room full of scientists that dying stars crush themselves into balls the size of a city, and the room laughed at him. In 1967, a 24-year-old graduate student noticed a quarter-inch of strange signal on 400 feet of chart paper, and her supervisor told her it was probably interference. And in 2000-2003, a teen at the University of Helsinki published a paper in Nature Communications calculating an 88% probability that the cores of the heaviest neutron stars contain a form of matter that has not existed freely in this universe since 1 microsecond after the Big Bang. That paper should have made headlines. It did not. These 3 moments are separated by decades, by continents, by entirely different branches of physics. But they are the same story, and that story ends with the most successful theory in the history of science staring at an object 12 kilometers wide and admitting it cannot tell you what is inside. Tonight, we are going from Fritz Zwicky's prediction to Jocelyn Bell Burnell's chart paper to a washing machine-sized X-ray telescope bolted to the outside of the International Space Station, to the death scream of 2 neutron stars ripping each other apart, 130 million light-years away. And by the end, the question you started with will not be the one keeping you up. So settle in, get comfortable. If you are not subscribed yet, join up. And if you want to go even deeper across physics, space, and the stranger corners of science, that is what the Patreon is for. Stay to the end of this one, because where the equation of state crisis actually leads is something that changes how you think about what the standard model can and cannot do. Let's start where it started. In 1934, a Swiss physicist named Fritz Zwicky stood in front of a room full of scientists at Stanford University and said something so audacious that several people in the audience laughed. He said that when a massive star dies, its core does not simply stop burning. It collapses. It collapses past the point where atoms can hold their shape, past the point where electrons can orbit, past the point where protons and neutrons can maintain their individual identities. It crushes itself into a ball roughly the size of Manhattan. And in that ball, matter reaches a density so extreme that a single teaspoon of it would weigh somewhere in the range of 4 to 6 billion metric tons. The audience did not take him seriously. The physics community filed his prediction under the category of colorful speculation and moved on. That was 92 years ago. And Fritz Zwicky was not a man the physics community was inclined to take seriously, not because of the quality of his ideas, which were decades ahead of his time, but because of his personality, which was decades behind in social grace. He was combative, abrasive, and openly contemptuous of colleagues he considered inferior, which was nearly everyone. He called other astronomers at Caltech spherical bastards, his reasoning being that they were bastards no matter which direction you looked at them. He filed grievances. He picked feuds. He once threatened to kill a fellow astronomer, though the context suggests this was bluster rather than genuine intent. His collaborator, Walter Bader, a German émigré with a quiet precision that was the opposite of Zwicky's chaotic intensity, was the one who presented the work at professional meetings, partly because Bader was better received, and partly because letting Zwicky address a room of peers was a calculated risk. But here is the thing about Zwicky that matters for this story. He was right about almost everything. He coined the term supernova. He predicted neutron stars. He proposed gravitational lensing as an observational tool decades before it was used. He predicted dark matter in 1933, a full year before the neutron star prediction, when he measured the velocity dispersion of galaxies in the Coma cluster and found that the visible mass was nowhere near sufficient to account for the observed motions. He called the missing mass Dunkel Materie, dark matter. It took 40 years for the rest of the field to accept it. A Los Angeles Times cartoon from January 19, 1934, reported his neutron star prediction with the kind of breathless amazement usually reserved for science fiction. Cosmic rays are caused by exploding stars, which burn with a fire equal to 100 million suns, and then shrivel from 500,000-mile diameters to little spheres 14 miles thick, says Prof. Fritz Zwicky, Swiss physicist. 14 miles, roughly 22 kilometers. He overestimated the diameter by about a factor of 2. The cartoon treated it as spectacle. The physics community treated it as noise. And 23 years later, when neutron stars were discovered, exactly where and how Zwicky said they would be, nobody gave him credit. The 1974 Nobel went to Hewish and Ryle for pulsars, not to Zwicky and Bardet, who predicted the objects that produce pulsars. 4 decades earlier, Zwicky died on February 8, 1974, the same year as the Nobel announcement, having never received the recognition his work deserved. The pattern is worth naming because it repeats. First, the idea is ridiculous. Then it is obvious. The one thing it can never be, apparently, is important at the moment when the person who proposed it could benefit from the recognition. And in the decades since, we have confirmed that Zwicky was right. Neutron stars are real. We have found over 3,000 of them. We have measured their masses and their spins and their magnetic fields. We have listened to the gravitational wave signal of 2 of them tearing each other apart. And here is the part that should unsettle you. After all of that, after 9 decades of observation and measurement and theoretical work, we still do not know what is inside them, not in the way you might think, where we have a rough idea and we are filling in details. We do not know in the way that matters. We do not know what form of matter exists at the center of a neutron star. We do not know what phase it occupies. We do not know what forces stabilize it. The densest observable matter in the entire universe, the one substance that pushes the laws of physics harder than anything else we can actually see. And we cannot tell you what it is made of. Not because we have not looked, but because when we looked, what we found does not match any known state of matter. And the people who understand this best have been quietly arguing about it for over 20 years, publishing papers in journals that almost nobody outside their field ever reads, while every popular science source on the planet keeps telling you the answer is neutrons. The answer is not neutrons. It was never just neutrons. And what it might actually be is something that has not existed freely in this universe since the first microsecond after the Big Bang. That sentence is going to take on a weight I cannot fully prepare you for. But we will get there. To understand why the interior of a neutron star represents the single largest unsolved problem in nuclear physics, you need to understand what happens to matter when you push it past the point where the rules stop working. And I do not mean past the point where the rules get complicated. I mean past the point where the rules, as we currently understand them, cease to produce answers that match what we observe. There is a difference. The first is a hard problem. The second is a crisis. And what is happening right now, in the space between observation and theory, is a crisis. Here is where it starts. You probably know the basic story. A star 8 to 25 times the mass of our sun exhausts its nuclear fuel. The core, no longer supported by radiation pressure, collapses under its own gravity in a fraction of a second. The outer layers are blown outward in a supernova. What remains at the center is a neutron star. And you were probably told, or you absorbed it from a documentary at some point, that a neutron star is essentially a giant atomic nucleus, that the collapse is so violent that electrons are forced into protons through a process called inverse beta decay, converting them into neutrons, and the entire remaining mass, roughly 1.4 times the mass of the Sun, is compressed into a sphere about 12 kilometers across, a city-sized ball of neutrons. That is not wrong exactly, but it is incomplete in a way that has been quietly breaking nuclear physics for the better part of 3 decades, because the description I just gave you is only accurate for the outer layers of a neutron star, the outer crust, maybe the outer core, the parts where the density is low enough, and I use that word relative to the absurdity we are about to enter, that our existing models of nuclear matter still produce reliable predictions. The deeper you go, the more those models fail. And at the center, at the very heart of the most extreme stable object in the observable universe, they do not just fail, they contradict each other. They contradict the observations. And in some cases, they contradict themselves. I want to be specific about what I mean by density here, because the numbers matter and they will keep mattering for the rest of this. Nuclear saturation density, the density inside a heavy atomic nucleus like lead or uranium, is roughly 2.7 times 10 to the 14th grams per cubic centimeter. That is already hard to wrap your mind around. If you could somehow scoop out a sugar cube-sized piece of a lead nucleus, it would weigh about 270 million metric tons. The outer core of a neutron star sits at roughly this density, maybe 1 to 2 times saturation density. The inner core, the region we are going to spend most of our time in, reaches 5 to 10 times nuclear saturation density, somewhere around 10 to the 15th grams per cubic centimeter. There is no material on Earth, no laboratory experiment, no particle accelerator, no nuclear detonation, no natural phenomenon short of a neutron star itself that produces cold, stable matter at this density. It does not exist anywhere else, and it has not existed freely in this universe since the temperature dropped below roughly 10 to the 12th Kelvin, which happened about 1 microsecond after the Big Bang. That is what I mean when I say we opened a neutron star. We did not cut one open with a knife. We measured it. We listened to it. We watched the X-rays it emits bend around its own gravitational field. And the picture that emerged from those measurements is something that the physics community has not been able to reconcile with any single model of matter. Not one. And the attempts to reconcile it have led to a conclusion that I still find difficult to sit with, which is that the cores of the heaviest neutron stars may contain a form of matter that does not consist of protons or neutrons at all. A form of matter where the quarks inside those particles have broken free of their confinement and rearranged themselves into something entirely different. Something that, if confirmed, would mean that right now, scattered across the galaxy, there are objects 12 kilometers wide that contain a substance the universe has not produced since the first heartbeat of creation. And nobody is talking about it. I need to take you through this properly, layer by layer, because the structure of a neutron star is not just a list of phases. It is a descent. Each layer deeper, the physics gets stranger, the models get less reliable, and the implications get harder to accept. And the thing I want you holding in your mind as we go is this. At every layer, the question is the same. What is holding this thing up? What is providing enough pressure to resist the gravitational collapse of 1.4 to 2.3 solar masses compressed into a space smaller than the city you are sitting in right now? At the surface, we know the answer. It is electron degeneracy pressure, the same thing that holds up white dwarfs. At the outer core, we know the answer. It is neutron degeneracy pressure, the Pauli exclusion principle applied to neutrons. At the inner core, past about twice nuclear saturation density, We do not know the answer. Something is providing pressure. Something is resisting collapse. And whatever it is providing more pressure than our best models of nuclear matter say should be possible. That is the crisis. That is the open question. And it is the question that every instrument and every gravitational wave detector and every theoretical calculation for the last 10 years has been circling without resolution. Let me start at the surface and take you down. The outer crust of a neutron star is the least exotic part, and even it is unlike anything you have encountered. It is a crystalline lattice. Picture a metal, but instead of iron atoms or copper atoms arranged in a grid, picture neutron-rich nuclei. Isotopes so far from the valley of stability that they could never exist on Earth, locked into a Coulomb lattice by the electrostatic forces between their protons, with a sea of degenerate electrons flowing between them, like the conduction electrons in a metal. The density here ranges from about 10 to the 4th grams per cubic centimeter at the surface, roughly the density of iron under extreme compression, to about 4 times 10 to the 11th grams per cubic centimeter at the bottom of the outer crust. This transition happens over maybe 300 to 500 meters, half a kilometer, and within that half kilometer, the nuclei get progressively more neutron-rich, absorbing electrons and converting protons to neutrons, becoming isotopes that our terrestrial nuclear physics tables have never catalogued. At 4 times 10 to the 11th grams per cubic centimeter, something happens that is called the neutron drip point. The nuclei become so bloated with neutrons that the neutrons begin to leak out. They drip free of the nuclear potential well and form a free neutron gas that coexists with the lattice. This is the beginning of the inner crust, and it extends for roughly another kilometer, maybe a bit less, down to about half of nuclear saturation density. The lattice is still there, but now the nuclei are swimming in a sea of free, superfluid neutrons. The neutrons have paired up through the attractive part of the nuclear force into Cooper pairs, the same kind of pairing that produces superconductivity in metals, and they flow without friction. This is neutron superfluidity, confirmed observationally in 2011 by Danny Page and collaborators at the National Autonomous University of Mexico, when they measured the cooling rate of the neutron star in the Cassiopeia A supernova remnant and found it was cooling faster than standard models predicted, consistent with the onset of neutron superfluidity in its core. But here is where it starts to get strange. In the deepest part of the inner crust, roughly the last 100 meters before the crust gives way to the core, the competition between the strong nuclear force, which wants to pull nucleons together, and the Coulomb force, which wants to push protons apart, produces shapes, not spheres. Shapes. The nuclei deform. They elongate into cylinders. They flatten into sheets. They develop holes. Physicists, with a kind of dark humor that only people staring at the limits of human knowledge develop, have named these phases after pasta, and I am not making this up. This is published, peer-reviewed nuclear physics. At relatively low density in this transition zone, the nuclei are roughly spherical, like gnocchi. As the density increases, they stretch into long cylindrical rods, spaghetti. Compress further and the rods merge into flat two-dimensional sheets, lasagna. Keep going and the sheets develop cylindrical holes through them, bucatini, or anti-spaghetti. And finally, just before the transition to uniform nuclear matter, the sheets close up into spheres of empty space inside a continuous nuclear medium, Swiss cheese. These are called nuclear pasta phases, and they were first proposed by Don Ravenhall, Chris Pethick, and Jim Wilson in 1983. The reason they matter is not the names. The reason they matter is that this thin layer of pasta, perhaps only 100 meters deep, may contain more mass than all the regular matter visible in the Milky Way's interstellar medium. And its material properties, its shear strength, its thermal conductivity, its response to stress, determine whether the neutron star's crust can crack during a star quake, which in turn determines whether we observe sudden spin-up events called glitches in pulsar timing data. I want to spend more time on the pasta, not because the names are amusing, though they are, but because the physics is telling you something about the nature of matter that you have probably never considered. At the densities where nuclear pasta forms, roughly 10 to the 14th grams per cubic centimeter, the system is caught in a competition between two forces with very different ranges. The strong nuclear force is attractive at intermediate distances, pulling nucleons together, but sharply repulsive at very short range, preventing them from collapsing onto each other. Its range is about 1 to 2 femtometers. The Coulomb force between protons is repulsive at all distances and falls off much more slowly. At lower densities, the strong force wins locally, forming compact spherical nuclei, while the Coulomb force keeps those nuclei separated from each other. But as density increases and the nuclei are pushed closer together, the Coulomb force between adjacent nuclei begins to compete with the strong force within them. The energy is minimized not by spheres anymore, but by shapes that reduce the surface area to volume ratio, while maintaining charge neutrality. This is the same physics that governs soap bubbles and cell membranes, except it is happening with nuclear matter at 100 trillion grams per cubic centimeter. The same geometric principles that determine the shape of foam in your kitchen sink determine the shape of matter in a neutron star crust. And that is not a metaphor. It is the actual mathematics. The competition between surface tension and bulk energy in a charged system produces precisely the sequence of minimal energy shapes that Ravenhall, Pethick, and Wilson predicted. Gnocchi, spaghetti, lasagna, bucatini, Swiss cheese, then uniform matter, a phase diagram of shapes driven by geometry and the fundamental forces. The pasta layer may be the strongest material in the universe. In 2018, Matthew Kaplan and Charles Horowitz at Indiana University published molecular dynamic simulations in Physical Review Letters, showing that nuclear pasta has a shear modulus up to 10 billion times stronger than steel. The breaking strain of the spaghetti phase exceeded that of any known material by many orders of magnitude. If the crust of a neutron star is going to crack, if a star quake is going to happen, it is the pasta layer that has to break. And when it does break, the energy released can produce the gamma-ray flares we observe from magnetars. The December 27, 2004 giant flare from SGR 1806-20, which released more energy in 1/10 of a second than the sun emits in 100,000 years, was likely triggered by a crust fracture that propagated through the pasta layer, a plate of spaghetti breaking at the bottom of a star that weighs more than the sun. And still, the pasta is just the crust. We have not reached the core. Everything I have described so far, all of it, is physics that is either well understood or at least well constrained by experiment. Everything from here forward is not, and we are still in the crust. We have not even reached the part where the physics breaks. Below the pasta, at about half of nuclear saturation density, the lattice dissolves entirely. You enter the outer core, and this is the region that corresponds to the standard picture you were given. A fluid of mostly neutrons, somewhere around 90 to 95%, with a small admixture of protons, electrons, and at higher densities, muons, all in a state called beta equilibrium, where the rates of neutron to proton conversion and proton to neutron conversion have reached a balance. The neutrons are superfluid. The protons, which carry charge, are not just superconducting, but form a type II superconductor, meaning the magnetic field is confined into quantized flux tubes rather than being expelled entirely. The outer core extends from half of saturation density to roughly 2 times saturation density, filling most of the volume of a neutron star and containing most of its mass. And this is where most textbooks stop. This is where the popular science version ends. Neutrons, some protons, superfluid, superconducting, done. And if you want to know what happens when a superfluid inside a neutron star disagrees with the crust it is trapped in, the answer is one of the most violent timekeeping events in astronomy, a glitch. The crust of a neutron star, locked into a rigid lattice, slows down over time as the pulsar loses rotational energy to electromagnetic radiation. But the superfluid neutrons in the inner crust and outer core are decoupled from the crust. They do not feel the electromagnetic braking directly. They keep spinning at their original rate, storing angular momentum. Over time, a velocity lag builds up between the superfluid and the crust. When the lag becomes too large, the superfluid suddenly transfers angular momentum to the crust in a catastrophic event that lasts less than a minute. The pulsar abruptly spins up, not by much, a fractional change in spin rate of about 1 part in a million for a typical Vela glitch. But the precision of pulsar timing is so extreme that this shows up as a sharp, unmistakable discontinuity in the arrival time of the pulses. The Vela pulsar glitches roughly every 3 years. The Crab pulsar glitches less regularly. And the size and frequency of glitches constrain how much superfluid is present in the star, which in turn constrains the equation of state. If too much of the star's moment of inertia is locked in the superfluid, the glitches would be bigger than observed. If too little, they would be smaller. The glitch data, combined with the mass and radius measurements, provides yet another independent constraint on the interior structure. And here is what makes glitches relevant to the deeper question. If the inner core undergoes a phase transition to quark matter, the superfluid properties change. The neutron superfluid in the outer core does not extend into a quark core. The CFL quark phase has its own superfluid component, but with different coupling to the crust, different relaxation timescales, different angular momentum transfer dynamics. A neutron star with a quark core would glitch differently than one without. The glitch behavior is a fingerprint of the interior, and the data, frustratingly, is not yet precise enough to distinguish the two scenarios. Everything points toward the same question. Everything leads to the same locked door. The density at the center is too high for our theories. The forces at play are too strong for our calculations. And the signatures we are looking for, in X-rays, in gravitational waves, in pulsar timing residuals, in glitch statistics, all carry information about what lies behind that door. But none of them, alone or in combination, have opened it yet. But the textbooks stop here because this is where the answers stop. Beyond roughly twice nuclear saturation density, you enter the inner core. And the inner core is the open wound in nuclear physics. It occupies perhaps the innermost 3 to 5 kilometers of a heavy neutron star. Its density reaches 5 to 10 times saturation density. And at those densities, something has to give. The question is what? There is something I need you to understand about the equation of state before we go further, because the term gets thrown around in physics communication as if it is self-explanatory, and it is not. An equation of state is a relationship between pressure and density. That is it. For any given density, how much pressure does the material exert? If you know that relationship, if you have a function that takes density as an input and gives pressure as an output, you can solve the Tolman-Oppenheimer-Volkoff equation and calculate the maximum mass and the mass-radius relation for neutron stars. The equation of state is the single missing ingredient. Everything else in the problem, general relativity, quantum mechanics, the Pauli exclusion principle, is known. The equation of state is the unknown. And the reason it is unknown is that it is not determined by any one force or any one interaction. It emerges from the collective behavior of trillions of strongly interacting particles at zero temperature and extreme density. It depends on the nucleon-nucleon interaction, which is itself an effective theory approximating the underlying quark-gluon dynamics. It depends on whether hyperons appear and at what threshold. It depends on whether a phase transition to quark matter occurs and whether that transition is sharp, first order, with a sudden jump in density at a critical pressure, or smooth, a crossover with a gradual change in the degrees of freedom. It depends on the symmetry energy of nuclear matter, the energy cost of converting protons to neutrons, which is constrained by laboratory experiments on neutron-rich nuclei, but only at 1 to 2 times saturation density. Above that, the symmetry energy is extrapolated. Every one of these dependencies carries uncertainty, and those uncertainties compound. The result is that at 5 times saturation density, the pressure predicted by different physically motivated models can differ by a factor of 2 or 3, and the maximum mass of a neutron star is exquisitely sensitive to the pressure at those densities. A 20% increase in pressure at 5 times saturation can raise the maximum mass by a quarter of a solar mass. The difference between a neutron star and a black hole is a 20% change in a number we cannot calculate from first principles. Let me give you a scale comparison that makes this visceral. Imagine you are an engineer designing a bridge. You know the load the bridge must support. You know the span. You know the material. What you do not know is the yield strength of the steel, and the available estimates for the yield strength vary by a factor of 2. Would you build the bridge? Would you drive across it? Because that is roughly the situation nuclear physics is in with neutron stars. The structural analysis is elegant. The observations are precise. The material properties are uncertain by a factor that would be unacceptable in any other branch of engineering or physics. And yet, the stars exist. The bridge is standing. Traffic is flowing. Something is holding it up. I need to tell you about a problem that has been tormenting nuclear physicists since the mid-1980s. It is called the Hyperon puzzle. And the reason it matters is that it is not a puzzle in the sense of something we are trying to figure out. It is a puzzle in the sense that the answer appears to be logically impossible, and yet the objects that embody the contradiction are spinning in the sky right now, observed and measured, refusing to not exist. Here is the problem. As you go deeper into a neutron star and the density climbs past about 2 to 3 times saturation density, the neutrons at the top of the Fermi sea become extraordinarily energetic. Their Fermi energy climbs above a threshold, and at that threshold, it becomes energetically favorable for a neutron to convert into a different particle entirely, a particle called a hyperon, specifically a lambda hyperon. The lambda has a mass of 1115 megaelectron volts, about 19% heavier than a neutron at 939.6 megaelectron volts. Under normal conditions, creating a lambda would cost energy. But in the ultra-dense environment of a neutron star inner core, the Fermi energy of the neutrons is so high that converting a neutron from the top of the Fermi sea into a lambda near the bottom of a new empty Fermi sea actually saves energy. It opens up a new degree of freedom. The system relaxes. And this is where the problem begins. Because when hyperons appear, they do something to the equation of state. They soften it. They reduce the pressure at a given density. And the reason is intuitive once you see it. The hyperons are draining energy from the top of the neutron Fermi sea and redistributing it into a new, lower energy channel. Less energy at the top means less Fermi pressure. Less Fermi pressure means less resistance to gravitational collapse. Run the calculation with standard hyperon-nucleon interaction models, and the maximum mass a neutron star can support drops from around 2.2 to 2.5 solar masses, which is what you get with pure nucleonic matter and realistic nuclear forces, to somewhere around 1.4 to 1.7 solar masses. 1.4 to 1.7. Think about that number. Think about what it means, because we have measured neutron stars that are heavier than that, not by a little, by a lot. In 2010, Paul Demarest and the team using the Green Bank telescope in West Virginia announced the mass of PSR J1614230, a millisecond pulsar in a binary system with a white dwarf companion, using the Shapiro delay, a general relativistic effect where the pulsar signal is delayed as it passes through the gravitational field of the companion. They measured a mass of 1.97 plus or minus 0.04 solar masses. That paper landed in Nature and it sent a shockwave through the neutron star community, because 1.97 is above the Hyperon threshold. If hyperons appear and soften the equation of state the way standard models predict, this star should not exist. It should have collapsed into a black hole. But it did not. 3 years later, in 2013, John Antoniadis and an international team published in Science the mass measurement of PSR J0348 plus 0432, a pulsar orbiting a white dwarf companion so tightly that the system completes a full orbit every 2.46 hours. They combined radio timing from the Effelsberg telescope with optical spectroscopy of the white dwarf from the Very Large Telescope in Chile, and derived a mass of 2.0, 1 plus minus 0.04 solar masses, firmly above 2, firmly above the Hyperon death line. And then in 2019, a result that took the problem from troubling to acute. Emmanuel Fonseca and the NanoGrav collaboration, using the Green Bank telescope and the Canadian Hydrogen Intensity Mapping Experiment, measured the mass of PSR J0740 plus 6620. This is a pulsar in a binary with another neutron star, and the Shapiro delay measurement was exquisite. The mass came back at 2.08 plus or minus 0.07 solar masses, updated from an earlier measurement by Heather Cromarty and colleagues in 2019 that had reported 2.14 with larger uncertainties, 2.08 solar masses. This is the heaviest, precisely measured neutron star in existence, and it should not be possible if hyperons do what every standard calculation says they should do. But wait, it gets worse. In 2022, Roger Ramani and collaborators at Stanford published a measurement of PSR J0952 0607, a pulsar called the Black Widow, because it is slowly devouring its companion star. Using optical light curve modeling from the Keck telescope in Hawaii, they estimated a mass of 2.35 plus or minus 0.17 solar masses. Now, this measurement is model dependent. It relies on assumptions about the shape and heating of the irradiated companion, and the error bars are large. But if the central value holds, this is a neutron star that weighs as much as 2 1/3 suns, and it spins at 707 Hz, 707 rotations per second. Its surface is moving at a significant fraction of the speed of light. Let me make sure the weight of this lands. The equations say hyperons should appear above 2 to 3 times nuclear saturation density. When they appear, the maximum mass drops to about 1.5. We observe stars at 2.0, 2.08, possibly 2.35 solar masses. Something is wrong with the equations, or something is wrong with our understanding of what matter does at those densities, or both. I want to stop here and tell you about the man who saw this problem 85 years before it had a name, because the story of how we got here is also a story about how physics handles its own blind spots. In 1939, 5 years after Zwicky's laughter prediction, J. Robert Oppenheimer and his graduate student George Volkoff at the University of California, Berkeley, published a paper in the Physical Review titled On Massive Neutron Cores. They used Richard Tolman's general relativistic framework for static, spherically symmetric fluid bodies and applied it to a star made entirely of non-interacting neutrons, a Fermi gas. No nuclear forces, no interactions, just neutrons packed together, obeying the Pauli exclusion principle and general relativity. Simultaneously, they derived what is now called the Tolman-Oppenheimer-Volkoff equation, the equation of hydrostatic equilibrium for a relativistic star, and when they solved it for their simplified neutron gas, they got a maximum mass of roughly 0.7 solar masses, 0.7, less than the Chandrasekhar limit for white dwarfs. In other words, their calculations said that neutron stars could not exist at any mass that was astrophysically relevant. A star massive enough to collapse past the white dwarf stage would be too heavy to be supported as a neutron star and would collapse all the way to what Oppenheimer and his student Hartland Snyder, in a separate paper that same year, described as continued gravitational contraction, what we now call a black hole. The paper was correct. The math was right. The physics was right for the assumptions they made. But the assumptions were wrong. They had left out the nuclear force. And the nuclear force, specifically its repulsive core at short range, provides enormous additional pressure at high density. It stiffens the equation of state. When realistic nuclear interactions were included by later researchers, the maximum mass climbed above 1.4, above 1.7, above 2.0, depending on which model you used and what assumptions you made about the interactions at supranuclear density. And this is the crux. The maximum mass of a neutron star is not determined by general relativity. It is not determined by the Pauli exclusion principle. Those provide the framework. The maximum mass is determined by the equation of state of cold, ultra-dense matter, and the equation of state is determined by whatever the strong nuclear force does at 5 to 10 times saturation density. And we do not know what the strong nuclear force does at those densities. Not with confidence, not without assumptions that amount to educated guesses layered on top of other educated guesses. Oppenheimer, for what it is worth, never returned to the problem. Within a few years, he was consumed by the Manhattan Project, and after the war, he never revisited neutron star physics. The Tolman-Oppenheimer-Volkoff equation became one of the most important equations in astrophysics, and the man it is named after spent less than a year thinking about it. He left the equation, and he left the problem embedded within it for other people to solve. They have been working on it for 87 years. They have not solved it, but they have gotten closer. And the way they got closer is one of the more remarkable convergences in the history of physics. In 2017, two things happened within weeks of each other that would transform neutron star physics from a field of theoretical speculation into a field of precision measurement. The first was the installation of an instrument on the International Space Station. The second was the death scream of two neutron stars 130 million light-years away. The instrument was called NICER, the Neutron Star Interior Composition Explorer. It was mounted on the outside of the ISS in June of 2017, a washing machine-sized X-ray telescope designed by Keith Gendreau at NASA Goddard with a single obsessive purpose: to measure for the first time both the mass and the radius of individual neutron stars, not the mass alone, which radio timing had been delivering for decades, not the radius alone, which had been estimated with enormous uncertainties from X-ray luminosity, both simultaneously from the same star. Because if you know both the mass and the radius, you can constrain the equation of state. You can start to narrow down what matter does at supranuclear density. You can start to figure out what is actually inside these objects. The way NASA does this is worth understanding because it is one of those ideas that sounds impossible until you hear the details, and then it sounds even more impossible, and then you realize it actually works. NASA watches millisecond pulsars. These are neutron stars that have been spun up to rotational periods of a few milliseconds by accreting matter from a companion star. Their surfaces are incredibly hot, around 1,000,000 Kelvin, but not uniformly hot. They have hot spots near their magnetic poles, regions where accreted matter has been funneled along magnetic field lines and has heated the surface. As the star rotates, these hotspots come into and out of view, producing a pulsed X-ray signal. Now here is the key. The X-ray photons emitted from those hotspots do not travel in straight lines. They travel through the curved space-time around the neutron star. And because the star is compact, its gravitational field is strong enough to bend the light paths significantly. Photons emitted from the far side of the star can be bent around and reach the observer. Photons emitted from near the limb of the star are gravitationally lensed. The result is that the shape of the X-ray pulse profile, the exact way the brightness varies as the star rotates, encodes information about the star's mass and radius. A more compact star, higher mass to radius ratio produces more gravitational lensing. The hotspot never fully disappears behind the star because the light bends around it. A less compact star produces less lensing. The hotspot fully disappears each rotation. By modeling the pulse profile with general relativistic ray tracing codes, you can extract the mass, the radius, and even the geometry of the hotspots. Two independent teams analyzed the first NASA target, PSR J0030 plus 0451, a millisecond pulsar spinning at about 205 Hz. Cole Miller's group at the University of Maryland, using a code called PDTU, reported in 2019 a mass of 1.4, 4 plus or minus 0.15 solar masses, and a radius of 13.02 plus or minus about 1.2 kilometers. Anna Watts' group at the University of Amsterdam, using a code called XPSI, reported a mass of 1.34 plus or minus 0.15 and a radius of 12.71 plus or minus about 1.1 kilometers. Two different teams, two different codes, two different statistical frameworks, and they agreed to within 5% on the radius. That alone was a triumph, but the surprise was the hotspot geometry. Every textbook picture of a pulsar shows two neat circular hotspots at the magnetic poles, antipodal, like the poles of a bar magnet. What NASA found was nothing like that. The data preferred a configuration with one small circular spot and one elongated crescent-shaped region, not antipodal, not symmetric, suggesting a magnetic field far more complex than a simple dipole. The crust of this neutron star is not organized the way the textbook says it should be. And that is a clue, because the magnetic field geometry is coupled to the interior physics, to the crust composition, to the superfluid and superconducting currents beneath the surface. If the field is not a dipole, the interior is not simple. Then came the measurement that the entire field had been waiting for. PSR J0740 plus 6620. The heavyweight 2.08 solar masses. Determined by radio timing, NASA turned its attention to this star, combining its data with observations from XMM Newton, the European Space Agency's X-ray satellite, to improve the background modeling. And in 2021, both teams published their results simultaneously. Miller's team reported a radius of 13.7, with error bars from plus 2.6 to minus 1.5 kilometers. Watts's team, led by Thomas Riley, reported 12.39 plus 1.3 minus 0.98 kilometers. Same star, same data, different analysis, and the central values differed by over a kilometer. Now, in a field where the entire width of the allowed equation of state corridor corresponds to a radius range of maybe 2 to 3 kilometers, a 1 kilometer disagreement between the two flagship analysis teams is not a minor detail. It is a structural problem, and it gets deeper. In 2024, both teams reanalyzed J0740 with 3.6 years of accumulated NASA data. Tuomo Salmi and colleagues from the Amsterdam group got 12.49 plus or minus about 1.1 kilometers. Alexander Dittman and Cole Miller got 12.92 plus 2.09 minus 1.13, which they narrowed to 12.76 when they capped their radius prior at 16 kilometers. Closer, but still not converged. And then a third star entered the picture and made things messier. PSR J0437-4715, the nearest and brightest millisecond pulsar, sitting just 157 parsecs from Earth. Vivek Chowdhury and collaborators published NASA results for this star in 2024. Mass from the Parkes pulsar timing array, 1.418 plus or minus 0.037 solar masses. Radius 11.36 kilometers, with uncertainties from plus 0.95 to minus 0.63. That is the tightest single-source radius constraint NASA has ever produced. And it is small, noticeably smaller than the J0030 results, possibly in tension with the J0740 results. If confirmed, it favors a softer equation of state, a universe where neutron star matter is more compressible, where the pressure rises less steeply with density. And that is the exact direction the Hyperon puzzle pushes, the exact direction where the problem gets worse, not better. I want to make sure you are tracking the architecture of this contradiction, because it is the thing that keeps nuclear physicists awake. The two solar mass pulsars demand a stiff equation of state at intermediate densities, roughly 2 to 4 times saturation density, because you need high pressure to hold up that much mass. But the NICER radius measurements and the gravitational wave constraints from GW170, 817, which I am going to get to in a moment, suggest the equation of state cannot be too stiff at those same densities, because the stars are not too large. The radii cluster around 12 kilometers, not 15. So you need high pressure, but not too high. Stiff, but not too stiff. The equation of state has to thread a needle, and the needle is getting narrower with every new measurement. And the Hyperon puzzle makes it worse still, because Hyperons soften the equation of state right in the density range where you need it to be stiff. So either Hyperons are being suppressed by some mechanism we do not fully understand, or they are appearing and something else is compensating for the softening. All the matter at those densities has undergone a phase transition into something that is not hyperonic at all, something for which the rules are entirely different. I promised you the death of 2 neutron stars, and it is time to deliver on that. On August 17th, 2017, at 12 hours 41 minutes and 4 seconds Coordinated Universal Time, the advanced LIGO detectors in Livingston, Louisiana and Hanford, Washington, along with the advanced Virgo detector in Cassina, Italy, recorded a gravitational wave signal designated GW170817. It was the 5th detection of gravitational waves overall, but it was the first from a binary neutron star in spiral. The combined signal-to-noise ratio was 32.4, the clearest gravitational wave signal detected to that point. The component masses were between 1.17 and 1.60 solar masses, with a total system mass of 2.74 solar masses. I want you to understand what happened in the minutes and hours after that detection, because it was one of those rare moments in the history of science where a single event reorganized an entire field. Within 1.7 seconds of the gravitational wave signal, the Fermi gamma-ray burst monitor detected a short gamma-ray burst, GRB 170-817A, from the same region of the sky. That was the confirmation that binary neutron star mergers are the engines behind short gamma-ray bursts, a connection that had been hypothesized for decades, but never proven. Within 11 hours, optical telescopes found the kilonova, a new point of light in the galaxy NGC 4993, about 40 megaparsecs from Earth. They designated it AT2017 GFO, and over the following days and weeks, 68 telescopes around the world observed it, watching its color evolve from blue to red as the material expanded and cooled. And what they saw in the spectra changed astrophysics. In 2019, Darach Watson and collaborators published in Nature the identification of the first individual heavy element in a kilonova spectrum, strontium, atomic number 38, created by the rapid neutron capture process, the R process, the nuclear reaction pathway that is responsible for approximately half of all elements heavier than iron in the universe: gold, platinum, uranium, thorium, elements so heavy that ordinary stellar fusion cannot produce them. For decades, the site of the R process had been debated. Was it supernovae? Was it neutron star mergers? The strontium in AT2017 GFO settled it. Neutron star mergers are an R process site. The gold in the ring on your finger, if you are wearing one, was forged in the collision of 2 dead stars in the same kind of event that produced GW170817. The neutron-rich ejector, roughly 5/100ths of a solar mass of material flung into space at 1/4 the speed of light, underwent rapid neutron capture in less than a second, building up heavy nuclei through a chain of neutron absorptions faster than the nuclei could beta decay back to stability. Let me tell you what it was actually like when GW170817 happened, because the clinical way I described it does not capture the human reality of that day. The signal arrived during the second observing run of advanced LIGO. The Virgo detector in Italy had just come online weeks earlier, adding a 3rd detector to the network for the first time. The signal lasted approximately 100 seconds. 100 seconds during which the 2 neutron stars, each roughly 12 kilometers across, spiraled from a separation of about 300 kilometers down to contact, accelerating from roughly 15% the speed of light to close to the speed of light. In the final milliseconds before merger, each star completed more than 1,000 orbits. 1,000 orbits in a few seconds, each orbit bringing them closer each orbit distorting them further under the tidal forces of their companion. The LIGO data analysis pipelines flagged the signal automatically. But the human response took longer to process, because it was not just a gravitational wave detection. Within 2 seconds, a notification went out to electromagnetic observatories worldwide, 70 observatories, across every wavelength of the electromagnetic spectrum, from radio to gamma ray, and they all turned to look. The gamma ray burst was detected 1.7 seconds after the gravitational wave signal. By Fermi, the optical counterpart was found within 11 hours by the Swope telescope at Las Campanas Observatory in Chile, independently spotted by several other teams within the hour. Over the following days, every major telescope on Earth, and several in space, observed the kilonova. I have read accounts from astronomers who were present during those days, and the consistent description is controlled chaos. Telescope time was reallocated on the fly. Schedules were torn up. People who had been sleeping were woken by phone calls. The paper that described the electromagnetic follow-up had nearly 4,000 authors, 4,000 scientists working across all wavelengths, across all continents, produced a multi-messenger portrait of a single astrophysical event. It was the first time in human history that an event was observed in both gravitational waves and light. And it told us things about neutron stars that a century of theoretical work had not been able to resolve. The spectroscopic evolution of the kilonova was like watching a periodic table being assembled in real time. The initial emission, the blue component, was powered by lighter R-process elements, materials with atomic numbers from about 30 to 50. The later emission, the red component, peaking days after the merger, was dominated by lanthanides and actinides, the heaviest elements produced by the R process, with atomic numbers reaching above 90. The opacity of these heavy elements, their ability to absorb and re-emit photons, gave the kilonova its characteristic red color and its slow decline. Kaysen and colleagues at Lawrence Berkeley National Laboratory estimated the total R-process ejecta at roughly 5/100ths of a solar mass, about 10 times the mass of Earth, of freshly synthesized heavy elements flung into interstellar space. And in 2024, Andrew Levin and collaborators identified tellurium, atomic number 52, in the kilonova spectra of a different event entirely, GRB 230307A, detected in March 2023. Tellurium, a metalloid used in solar panels and thermoelectric devices, forged in the collision of two dead stars and identified in its spectral signature from 750 million light-years away. The gold in your wedding ring, the iodine in your thyroid gland, the xenon in your car headlights. All of it was cooked in events like GW170817. In the neutron-rich fireball of two compact objects, each containing matter in a phase we cannot identify, tearing each other apart and spraying heavy elements into the galaxy. You are, in a very literal sense, made of neutron star debris, and the process that made the atoms in your body was powered by the same equation of state, whose nature we cannot determine. The strong force at supranuclear density is not an abstract concern. It is the reason the periodic table extends past iron. It is the reason you have bones and blood and hemoglobin. The physics we do not understand is the physics that made you possible. But the gravitational wave signal itself carried something even more precious than the kilonova. It carried information about the interior of the neutron stars. During the final orbits of a binary neutron star in spiral, as the two stars spiral closer and closer, they begin to deform each other. The tidal gravitational field of each star raises a bulge on the other, just as the moon raises tides on Earth. The key difference is that the deformability of a neutron star How much it bulges in response to an external tidal field depends on its internal structure. A star made of stiff matter, high pressure at a given density, resists deformation. It stays relatively spherical. A star made of soft matter, lower pressure, bulges more, deforms more easily, and that deformation affects the gravitational wave signal. It changes the rate at which the orbit decays. It introduces a correction to the waveform that accumulates over the last several hundred orbits. The LIGO and Virgo collaboration extracted this tidal deformability, designated lambda, from the GW170-817 signal. The initial result, published in Physical Review Letters in October 2017, put an upper bound of lambda less than 800 at 90% confidence. In 2018, using improved waveform models and assuming both stars obey the same equation of state, they tightened this to lambda at 1.4 solar masses equals 190, with an asymmetric uncertainty from plus 390 to minus 120. That number, 190, is a direct measurement of how squishy a 1.4 solar mass neutron star is. And it told us that neutron stars are not too stiff. Combined with the mass constraint from the 2 solar mass pulsars, which says they cannot be too soft, the equation of state was being squeezed from both sides. Emeli Anala, Tyler Gorda, Aleksi Kokela, and Aleksi Vuorinen at the University of Helsinki published a paper in Physical Review Letters in 2018, just weeks after the GW170-817 tidal measurement, showing that the combined constraints put the radius of a 1.4 solar mass neutron star at less than 13.6 kilometers, immediately ruling out the stiffest families of equations of state, paired with a multi-messenger analysis by Tim Dietrich, Michael Coughlin, and collaborators in Science in 2020. The combined NICA plus gravitational wave plus nuclear theory constraint converged on a radius of 11.75 kilometers, plus or minus about 0.8, roughly 12 kilometers. So there it is. The densest stable matter in the universe lives inside an object 12 kilometers wide. We can measure the size of that object to within about a kilometer. We can weigh it to within a few hundredths of a solar mass, and we still cannot tell you what the matter at its center is made of. That is not a gap in knowledge. That is a failure of the theory of nuclear matter at high density. The strongest force in nature, the force that holds every nucleus in your body together, is the force we understand the least in the regime where it matters the most. I want to tell you about the woman who made all of this possible. Not NICA, not the gravitational wave detectors, but the very concept that neutron stars are real, observable objects. Because her story is also a story about what the physics community does with people who find things they were not supposed to find. In the summer of 1967, a 24-year-old Irish graduate student named Jocelyn Bell was operating a radio telescope she had spent 2 years helping to build, the Interplanetary Scintillation Array at the Mullard Radio Astronomy Observatory in Cambridge, England. 4.5 acres of wooden poles and copper wire. She was working under Anthony Hewish, and her job was to operate the telescope and analyze the data, which arrived on chart paper, 100 feet of chart paper per day, which she reviewed by eye, marking features of interest with a red pen. On August 6, 1967, she noticed what she would later describe as a bit of scruff, a 1/4 inch of unusual signal in 400 feet of trace. Most people would have dismissed it as radio interference, and in fact, her supervisor initially did. But Bell persisted. She kept watching for the signal. On November 28th, using a high-speed chart recorder to resolve the signal in time, she found it. A series of perfectly regular pulses, 1.337 seconds apart, arriving from a fixed point in the sky. The regularity was so precise that the team briefly considered the possibility that it was an artificial signal. They designated the source LGM-1, Little Green Men-1. Bell has described the period with characteristic understatement. I was a bit cross about the possibility that it was little green men, because it would mess up my thesis. Within weeks, she found 3 more pulsing sources at different positions in the sky, ruling out an artificial origin. The discovery was published in Nature on February 24, 1968. 5 authors, Hewish, Bell, Pilkington, Scott, and Collins, in that order. Franco Pacini, an Italian astrophysicist working at Cornell, had actually predicted months before Bell's discovery that a rapidly rotating, strongly magnetized neutron star would emit electromagnetic radiation. His paper was published in Nature in 1967, before the pulsar announcement. Thomas Gold at Cornell independently proposed the rotating neutron star lighthouse model in 1968. Their offices were practically adjacent. They did not realize their overlap until after publication. The Pacini-Gold model predicted that pulsars should gradually slow down as they radiate away rotational kinetic energy. A prediction confirmed when the Crab pulsar was found to be lengthening its period at about 36.4 nanoseconds per day. In 1974, the Nobel Prize in Physics was awarded to Anthony Hewish and Martin Ryle for the discovery of pulsars. Jocelyn Bell was not included. She was 24 at the time of the discovery, a graduate student, and the Nobel Committee decided that the prize should go to the supervisors rather than the student. Fred Hoyle publicly criticized the decision. The physics community has debated it ever since. Bell herself has been notably gracious about it, publicly stating that the decision was defensible given the norms of the time. But let me tell you what happened in 2018. The Breakthrough Prize in Fundamental Physics, carrying an award of $3 million, roughly £2.3 million, was given to Jocelyn Bell Burnell for her discovery of pulsars, 50 years late. And she donated every penny of it. She established the Bell Burnell Graduate Scholarship Fund at the Institute of Physics, supporting women, underrepresented minorities, and refugees pursuing physics PhDs in the United Kingdom. The woman who was passed over for the Nobel used the money she eventually received to make sure that no one else would have to fight as hard as she did. I am telling you this not as background. I am telling you because without Bell, without that quarter-inch of scruff on 400 feet of chart paper, there would be no pulsars. Without pulsars, there would be no radio timing measurements. Without radio timing, we would not know that neutron stars exceed 2 solar masses. Without that mass measurement, we would not know that the equation of state has a problem. Without the problem, there would be no crisis. Every measurement I have described in this video traces back, in one way or another, to a 24-year-old woman in a field in Cambridge in 1967 who refused to ignore a signal that everyone else thought was noise. And here is where the descent goes deeper than the Hyperon puzzle. Because the Hyperon puzzle assumes that the matter at supranuclear density is still composed of baryons. Neutrons, protons, hyperons, particles made of 3 quarks held together by the strong force. But there is another possibility, one that the data is increasingly pointing toward, and one that most popular science sources have either never mentioned or glossed over entirely. The quarks might be free. In ordinary matter, quarks are confined inside baryons. An up quark, an up quark, and a down quark make a proton. An up quark and 2 down quarks make a neutron. The strong force, mediated by gluons, becomes stronger as you try to pull quarks apart. This is called confinement. You cannot isolate a single quark under normal conditions. It is one of the most fundamental features of quantum chromodynamics, the theory of the strong force. But confinement has a limit. At sufficiently high temperature or density, the interactions between quarks weaken due to a property called asymptotic freedom, which is the opposite of what happens at low energy. At extreme conditions, the barriers between individual baryons dissolve. The quarks stop belonging to specific protons or neutrons and begin to move freely through the medium. This is called deconfinement, and the resulting state of matter, a plasma of free quarks and gluons, is called quark-gluon plasma. You have probably heard of quark-gluon plasma in the context of particle accelerators. At the relativistic heavy ion collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN, physicists smash heavy nuclei together at enormous energies. Gold on gold at RHIC, lead on lead at the LHC. The collisions create tiny fireballs with temperatures exceeding 10 to the 12th Kelvin, roughly 100,000 times hotter than the center of the sun. And in those fireballs, for about 10 to the minus 23 seconds, quarks and gluons move freely. But here is the thing that almost nobody tells you. The quark-gluon plasma at RHIC and the LHC is the wrong kind. It is hot quark-gluon plasma, high temperature, low net baryon density. The quarks are free because the thermal energy overpowers the confining force. Neutron star cores are the opposite. They are cold. The thermal energy is negligible compared to the Fermi energy. The temperature inside a neutron star core, even for a young one, is around 10 to the 8th to 10 to the 9th Kelvin, which sounds high until you realize that the Fermi energy of the particles is around 100 megaelectronvolts, equivalent to a temperature of about 10 to the 12 Kelvin. The matter is effectively at zero temperature for the purposes of the equation of state. Deconfinement in a neutron star core, if it happens, is driven not by heat, but by density, by pure compression. And this is the part that should concern you. Hot quark-gluon plasma and cold dense quark matter live in completely different regions of the QCD phase diagram. Temperature on the vertical axis, baryon chemical potential on the horizontal. Colliders explore the upper left, neutron stars explore the lower right, and the theoretical tool that would let us calculate the properties of matter in the lower right, lattice quantum chromodynamics, the gold standard for first principles QCD calculations, does not work there. It suffers from what is called the fermion sign problem. At non-zero baryon chemical potential, the path integral becomes complex, the statistical sampling methods fail, and the calculation becomes computationally intractable. You cannot lattice QCD your way to the equation of state of neutron star matter. Not now. Not with any foreseeable advance in computing. The sign problem is not a technical obstacle. It is a mathematical barrier. Let me walk you through the QCD phase diagram because it is the single most important picture in all of nuclear and particle physics, and almost nobody outside the field has ever seen it. Draw a graph. Horizontal axis is baryon chemical potential, which you can think of as a measure of the net density of baryons, protons plus neutrons in the system. Vertical axis is temperature. At the origin, zero density, zero temperature, you have the vacuum, empty space. Move up along the vertical axis, increasing temperature at zero density, and you pass through the hadronic gas phase. Then, through a smooth crossover at around 155 megaelectronvolts, roughly 1.8 times 10 to the 12th Kelvin, into the quark-gluon plasma. This crossover is well established by lattice QCD, which works perfectly at zero baryon chemical potential. The ALICE experiment at CERN has studied this region extensively. The physics is reasonably well understood. Now move to the right along the horizontal axis. Increase the baryon density at zero temperature. You pass through nuclear matter at saturation density, then through progressively denser matter at some critical density. Theory suggests you should transition from hadronic matter to quark matter. But the nature of that transition is one of the great open questions in physics. Is it a first-order phase transition with a sharp boundary, a latent heat, a discontinuity in density at a fixed pressure? Or is it a smooth crossover, like the temperature-driven transition at zero density, where the degrees of freedom gradually change from hadrons to quarks without any discontinuity? If the transition is first order, there should be a critical endpoint somewhere in the phase diagram, a specific temperature and density where the first order line terminates and becomes a crossover. Finding this critical endpoint is one of the stated scientific goals of the Beam Energy Scan program at RHIC, which has been systematically lowering the collision energy to probe higher baryon densities and lower temperatures, trying to sweep across the phase diagram toward the region where the critical point might live. But here is the problem that almost never gets stated clearly in popular treatments. The Beam Energy Scan at RHIC probes the phase diagram at finite temperature. Neutron star cores live at effectively zero temperature. The critical endpoint, if it exists, is somewhere in between. And the trajectory from the RHIHE energy scan to neutron star conditions requires extrapolation across a region of the phase diagram where no experimental data exists and no first principles calculation is possible. The sign problem blocks lattice QCD at finite baryon density. The Monte Carlo methods that work at zero density produce complex weights at finite density, making important sampling fail. Every method that has been proposed to circumvent the sign problem, Taylor expansion, reweighting, complex Langevin, the density of states method has its own limitations, and none has solved the problem in full QCD at physical quark masses. This is not a temporary computational bottleneck. There is no Moore's law solution. The sign problem is exponentially hard. Doubling your computer does not halve the problem. It is a qualitative barrier, not a quantitative one. And until it is solved, or circumvented by some method nobody has yet invented, the equation of state of cold dense quark matter will remain inaccessible to first principles theory, which means neutron stars are not just laboratories. They are the only experiment, the only data, the only window into the lower right corner of the QCD phase diagram, and the observations are our calculations. The mass and radius measurements from NICER, the tidal deformability from LIGO, the maximum mass from pulsar timing, these are not supplements to theory, they are substitutes for it. In the absence of calculability, observation becomes the foundation rather than the test. I do not know if the physics community fully reckons with how unusual this situation is. In almost every other area of fundamental physics, theory leads and experiment confirms. You predict the Higgs boson, you build the LHC, you find it. You calculate the anomalous magnetic moment of the electron, you measure it to 13 decimal places, they agree. But for the equation of state of cold dense matter, the direction is reversed. The observations are ahead of the theory. NICER and LIGO are measuring something that QCD cannot predict. The data exists. The framework to interpret it at a fundamental level does not. That should bother you, not because it is a failure, but because it reveals a limit, a genuine structural limit in the most successful theory of the strong force ever constructed. So, We cannot recreate cold, ultra-dense matter in any laboratory. We cannot calculate its properties from first principles. The only place in the observable universe where it exists is inside neutron stars, hidden behind a gravitational field so strong that the escape velocity is roughly 40% the speed of light. And the only way to probe it is by measuring the mass, radius, spin, and tidal deformability of these objects from thousands of light years away, and working backward from those bulk properties to the microscopic physics of the core. This is what I mean when I say we opened a neutron star. We did not cut it open. We read its shadow. And what the shadow says is that something unexpected is happening inside. In 2020, Emeli Anala, Tyler Gorda, Alexei Kirkala, Jonas Natila, and Alexei Vuorinen published a paper in Nature Physics titled Evidence for Quark Matter Cores in Massive Neutron Stars. The paper used a model-independent approach. They started with chiral effective field theory, which provides reliable predictions for nuclear matter up to about 1 to 2 times saturation density, and perturbative QCD, which provides reliable predictions at asymptotically high density, dozens of times saturation density, far above what exists in any neutron star. Between those two anchors, at the densities relevant to neutron star cores, the equation of state is unknown, so they interpolated. They generated millions of possible equations of state that smoothly connected the low-density regime to the high-density regime, subject to the constraint that they must support at least 2 solar mass stars and be consistent with the GW170817 tidal deformability measurement. What they found was that for neutron stars near the maximum mass, the equation of state in their cores exhibits characteristics that are inconsistent with normal hadronic matter. Specifically, the speed of sound in the core approaches a value called the conformal limit, where the speed of sound squared equals 1/3 of the speed of light squared. In ordinary nuclear matter, the speed of sound is higher than this. In quark matter, at extreme density, the speed of sound approaches this limit from below, and the polytropic index, a measure of how stiff the equation of state is, drops below 1.75 in the core, which is characteristic of deconfined matter. This was not a detection. I want to be clear about that. It was evidence, statistical evidence that the matter in the cores of the heaviest neutron stars behaves more like free quarks than like confined baryons. The paper was careful, the language was measured, but the implication was not. 3 years later, in 2023, Anala and colleagues followed up with a paper in Nature Communications titled Strongly Interacting Matter Exhibits Deconfined Behavior in Massive Neutron Stars. This time, they used a full Bayesian framework incorporating updated NICE data and gravitational wave constraints. They quantified the posterior probability that maximally massive neutron stars contain deconfined quark matter at roughly 80 to 90%. The paper reported approximately 88% credence. In their words, they demonstrated that at the highest densities probed, the equation of state is consistent with quark matter by establishing approximate conformal symmetry restoration with high credence and showing that the number of active degrees of freedom is consistent with deconfined matter. 88%. Let me make sure you understand what that means and what it does not mean. It means that according to a Bayesian analysis incorporating everything we know from nuclear theory, X-ray timing, and gravitational waves, there is roughly a 9 in 10 chance that the cores of the heaviest neutron stars are not made of neutrons or protons or hyperons at all. They are made of quark matter, free quarks, possibly in a color superconducting phase where quarks pair up through the strong force in a phenomenon analogous to superconductivity in metals, a state of matter that was first described theoretically by Mark Alford, Krishna Rajagopal, and Frank Wilczek in 1999. What it does not mean is that this is confirmed. It is Bayesian credence, not experimental detection. The analysis depends on assumptions. The interpolation method has its own biases. Competing analyses using different frameworks produce different posterior probabilities. There are perfectly respectable groups who argue that repulsive three-body forces between hyperons and nucleons, as demonstrated by Diego Lonardoni and collaborators in 2014, using quantum Monte Carlo methods, and by Thorsten Gersten, Norbert Kaiser, and Wolfram Weisse in 2020, using chiral effective field theory, can resolve the Hyperon puzzle without invoking quark deconfinement at all. The three-body forces provide enough additional repulsion to suppress hyperons or compensate for their softening. Both resolutions remain on the table. But here is the thing that neither side disputes. Here is the consensus that emerges from every group, every method, every interpretation. The equation of state of cold, ultra-dense matter is not known. The densest observable matter in the universe is the least understood, and whatever stabilizes neutron stars above two solar masses, whether it is repulsive three-body forces or quark deconfinement or some combination of both, it is operating in a regime where our fundamental theory of the strong force cannot make first principles predictions. The standard model of particle physics, the most precisely tested theory in the history of science, loses its predictive power at exactly the densities found in neutron star cores. Not at the Planck scale, not at the singularity of a black hole, not in some exotic hypothetical scenario, in objects that we can see, in objects that we have measured the mass and radius of, in objects that are spinning in our own galaxy right now. I need to tell you about the color superconducting phases, because they represent one of the most remarkable predictions in all of theoretical physics, and almost no popular science source has ever described them accurately. At asymptotically high baryon density, QCD is unambiguous about what happens. Quarks, liberated from confinement, interact via the strong force, which at high density has a weakly attractive component in the color antitriplet channel. This means quarks can form Cooper pairs, just as electrons form Cooper pairs in a superconductor. But quarks come in 3 colors and multiple flavors, and the pairing pattern determines the phase. The most symmetric phase is called the color flavor locked phase, or CFL. In this state, all 3 light quark flavors, up, down, and strange, pair with each other in a pattern that locks color rotations to flavor rotations. Every color pairs with every flavor. The result is a condensate that breaks both the color gauge symmetry and the approximate chiral symmetry of QCD simultaneously. The CFL phase is remarkable for several reasons. It is a superfluid. It is a color superconductor, meaning color magnetic fields are expelled from its bulk, and it is electrically neutral without needing any electrons at all, which means it can fill the entire core of a neutron star without requiring a compensating electron gas. At intermediate densities, where the strange quark mass of about 95 megaelectronvolts starts to matter, the pairing pattern may change. The 2-flavor superconducting phase, or 2SC, involves only up and down quarks pairing, leaving strange quarks unpaired. But Alford and Rajagopal argued in 2002 that electrical and color charge neutrality requirements in a compact star make the 2SC phase unlikely to fill macroscopic volumes. The transition from normal hadronic matter to quark matter may go directly to the CFL phase, or it may pass through exotic intermediate states, like the crystalline Loff phase, where Cooper pairs carry non-zero total momentum, and the condensate forms a crystalline structure in position space. And there is another layer to the color superconductivity story that I have not told you yet. And I think it matters because it illustrates just how strange the predictions for neutron star cores have become. In the CFL phase, the color superconducting condensate breaks a global symmetry of QCD called baryon number symmetry. When a continuous symmetry is spontaneously broken, Goldstone's theorem guarantees the existence of a massless excitation. In the CFL case, this massless mode is a superfluid phonon. The CFL phase is not just a superconductor. It is simultaneously a superfluid. It flows without friction, and the magnetic field behavior is equally exotic. In an ordinary type 2 superconductor, like the proton fluid in the outer core, magnetic flux is confined to quantized vortex tubes, each carrying a quantum of magnetic flux. In the CFL phase, the color magnetic flux is confined in a similar way, but the flux tubes carry color magnetic flux, not ordinary electromagnetic flux. The CFL phase is transparent to ordinary electromagnetic fields, but opaque to color magnetic fields. Now consider what this means for the structure of a neutron star. If a CFL core exists, the outer core is a neutron superfluid coexisting with a proton type 2 superconductor. The ordinary magnetic field is threaded through it in quantized flux tubes. As the star rotates, the superfluid component forms quantized vortex lines, each carrying a quantum of angular momentum. The interaction between the magnetic flux tubes and the superfluid vortices is what governs the long-term spin evolution of the pulsar, the glitches, and the breaking index. But if the inner core transitions to CFL quark matter, the magnetic flux tubes from the outer core encounter a phase boundary. The CFL phase does not support ordinary electromagnetic flux tubes. What happens at that boundary? Do the flux tubes terminate? Do they convert into a different kind of topological defect? Do they cause the magnetic field to be expelled from the quark core entirely, concentrating it in the hadronic outer core and producing a stronger surface field than you would otherwise expect? These questions are not theoretical curiosities. They have observable consequences. The magnetic field geometry of a neutron star determines its spin down rate, its pulse profile, its emission spectrum. If CFL quark matter in the core alters the magnetic field distribution, it would show up in the data. And in fact, some of the anomalies that NICER has observed, the non-dipolar hotspot geometries, the asymmetries that defy the simple textbook picture, could be signatures of exotic core physics leaking outward through the magnetic field. Could be. We do not know. The modeling is not there yet. The data is suggestive, but not conclusive. And the theoretical predictions for how a CFL core would modify the surface magnetic field depend on the details of the hadron-quark interface, which is yet another thing we cannot calculate from first principles. Layer after layer after layer, every answer opens a deeper question. Every measurement constrains the problem without solving it. And every theoretical prediction requires assumptions about physics in a regime where our ability to make reliable assumptions has been exhausted. I spoke earlier about the three-body Hyperon-nucleon forces as one possible resolution to the Hyperon puzzle. And I want to give you the details of that work because it represents the competing explanation to quark deconfinement. And the tension between these two camps is one of the most consequential unresolved disputes in nuclear physics. The idea is straightforward. In a free space, a lambda hyperon and a neutron interact through a two-body force, attractive at intermediate range, repulsive at very short range, broadly similar to the neutron-neutron interaction, but weaker and less well constrained by scattering data. Hyperon-nucleon scattering experiments are extraordinarily difficult because hyperons are unstable, A free lambda lives for about 2.6 times 10 to the minus 10 seconds before decaying. You cannot make a target out of hyperons. You cannot store them. You have to produce them in collisions and measure their interactions in flight, which means the data is sparse and the error bars are large. But in the dense environment of a neutron star, there is a three-body effect. When a lambda is surrounded by multiple nucleons, the three-body force between the lambda and two nucleons can provide additional repulsion that is absent in the two-body interaction. Diego Lonardoni and collaborators demonstrated this in 2014, using auxiliary field diffusion Monte Carlo simulations, a computational technique that handles quantum many-body systems with controlled approximations. They showed that depending on the strength of the lambda-nucleon-nucleon three-body force, which is constrained by hypernuclei data but only loosely, the onset of hyperons can be delayed to higher densities, and the softening of the equation of state can be partially or fully compensated. In 2020, Thorsten Gerstung, Norbert Kaiser, and Wolfram Weiser took a different approach, using chiral effective field theory extended to SU-3 flavor symmetry. Their framework included not just nucleon-nucleon-nucleon three-body forces, which are well established in nuclear physics, but also Hyperon nucleon-nucleon forces with a strength determined by SU-3 symmetry relations and the measured properties of hypernuclei. Their finding was striking. They concluded that the combined repulsive effects of two- and three-body correlations can make the appearance of lambda hyperons in neutron stars energetically unfavorable, meaning the three-body forces could suppress hyperons entirely up to the densities found in two solar mass stars. No hyperons, no softening, no puzzle. If this is correct, then there is no need for quark deconfinement to explain the observed masses. The hadronic equation of state with realistic three-body forces can support two solar mass stars without any exotic phases. The cores of neutron stars are made of neutrons, protons, and possibly a few hyperons, all the way down. Remarkable, mundane, and entirely consistent with the data. But the Analar Group's analysis, which finds 88% credence for quark matter cores, does not assume any specific model for the hadronic interactions. It works from general thermodynamic constraints. And its conclusion is that the behavior of the equation of state at the highest densities probed by maximally massive neutron stars, the way the speed of sound approaches the conformal limit, the way the number of degrees of freedom increases, looks like deconfined matter, not hyperonic matter, not nucleonic matter with three-body forces. Quark matter. Both camps have published in Nature or Nature subsidiary journals. Both camps use state-of-the-art methods. Both camps are led by serious, respected groups, and they reach opposite conclusions about what is inside the densest observable objects in the universe. This is not a case where one side is fringe and the other is mainstream. This is the mainstream disagreeing with itself at the highest level. And I personally think this is underrated. I think the fact that we genuinely do not know whether the cores of neutron stars are hadronic or quark, that the answer to this question depends on the outcome of a methodological and philosophical debate between two legitimate schools of nuclear physics, and that the resolution may require a third-generation gravitational wave detector that has not been built yet, is one of the most significant open questions in all of science, and it receives approximately 1% of the public attention that dark matter and dark energy do. The periodic table of elements does not have a line item for the stuff at the center of a neutron star. There is no entry for color superconducting quark matter. If it exists, it is the most common form of exotic matter in the galaxy. There are roughly 1 billion neutron stars in the Milky Way. If the heaviest ones all contain quark cores, there may be more quark matter in the galaxy than all the gold and platinum and uranium combined. An entire phase of matter, possibly filling the cores of 1 billion dead stars, and we cannot confirm its existence because the calculation that would do so is mathematically intractable. This was published. It has been sitting in the literature for years. It should have been front-page news. It was not. I want you to sit with this for a moment. We are talking about a crystal made of paired quarks, not atoms, not molecules. Quarks, locked into a spatial lattice by the dynamics of the strong force. Inside an object 12 kilometers wide, spinning hundreds of times per second, 100 light years from Earth. And the theoretical framework that predicts this crystal is the same framework, quantum chromodynamics, that cannot calculate whether it actually forms at the relevant densities. The reason all of this matters, the reason it is not just an academic curiosity, is that the phase of matter at the center of a neutron star determines the maximum mass. It determines whether the star lives or dies. The equation of state at 5 to 10 times saturation density sets the Tolman-Oppenheimer-Volkoff limit, and the TOV limit is the boundary between neutron stars and black holes. It is the line that separates the densest observable matter from the unobservable abyss of a singularity. Get the equation of state wrong, and you cannot predict where that line falls. You cannot predict what happens to the core of a massive star when it collapses. You cannot predict whether a given binary merger produces a neutron star or a black hole or something in between. And something in between is not a figure of speech, because LIGO has found objects that live in the gap. In June of 2020, the LIGO-Virgo collaboration published the detection of GW 190814, a gravitational wave event from August 14th, 2019, a merger between a 23 solar mass black hole and a compact object weighing 2.5 to 2.7 solar masses. That secondary object sits in what had been called the mass gap, the mysterious void between the heaviest neutron stars at around 2 to 2.3 solar masses and the lightest known black holes at around 5 solar masses. For decades, X-ray binary observations had suggested this gap was real, that some feature of supernova explosions prevented compact remnants from forming in this range. The secondary in GW 190814 blew that picture apart. It is either the lightest black hole or the heaviest neutron star ever detected in a compact binary. If it is a neutron star at 2.6 solar masses, it would require an equation of state stiffer than almost any model predicts, or it would need to be rapidly rotating to support the additional mass. Most analyses favor it being a black hole, but nobody is certain. Then in May of 2023, LIGO detected GW 230529, a merger between a compact object of about 3.6 solar masses, sitting squarely in the mass gap, and a likely neutron star of about 1.4 solar masses. The result was announced in April 2024, and Michael Zevin at Northwestern's Center for Interdisciplinary Exploration and Research in Astrophysics framed it as evidence that the mass gap may not exist at all, that the clean boundary between neutron stars and black holes is a fiction imposed by the limitations of our electromagnetic observations. And if the mass gap is not empty, then the TOV limit, the maximum neutron star mass, is even more uncertain than we thought. And the equation of state, the thing that sets it, is even more unconstrained. The problem does not simplify. It ramifies. There is a measurement I have not told you about yet, because I wanted to save it for this part of the story. It concerns the fastest spinning neutron star ever found, and it connects to the equation of state in a way that tightens the noose on every model simultaneously. PSR J174-82446 AD, a pulsar in the globular cluster Terzan 5, discovered by Jason Hessels and collaborators and published in Science in 2006. It spins at 716 Hz, 716 rotations per second. Its equatorial surface velocity exceeds 70,000 kilometers per second, roughly 24% the speed of light. The reason this star matters for the equation of state is geometrical. A spinning neutron star is not spherical. It is oblate. The centrifugal force pushes material outward at the equator, distorting the star into a flattened shape. And for any given equation of state, there is a maximum spin rate beyond which the centrifugal force at the equator exceeds the gravitational binding, and the star flies apart. That maximum spin rate depends on the mass, the radius, and the equation of state. Soft equations of state, which produce smaller, denser stars, allow higher spin rates because the material is more tightly bound. Stiff equations of state, producing larger, less compact stars, have lower breakup frequencies. At 716 Hz, PSR J1748-2446, AD is spinning fast enough that it constrains the equation of state from the rotational side. The EOS must be compatible with a star that can support this spin rate without shedding mass, and it must simultaneously support two solar mass stars. These are not the same constraint. A very soft EOS supports fast spins but cannot reach two solar masses. A very stiff EOS easily supports two solar masses but may not allow 716 Hz without breaking. The equation of state has to satisfy both. The corridor narrows further, and there is something else about this star, something that connects to the quark matter hypothesis in a way that I find deeply unsettling. If the core of this pulsar underwent a phase transition to quark matter, at some point during its spin-up period, the sudden change in the equation of state would alter the moment of inertia. A phase transition that softens the core would cause the star to contract slightly, conserving angular momentum, and spin up even faster. A phase transition that stiffens the core would cause it to expand slightly and spin down. The spin evolution of millisecond pulsars, if measured with sufficient precision over long enough baselines, could in principle reveal the presence of a phase transition. The spin is a probe of the interior. The rotation rate is a seismograph for the soul of the star. Nobody has detected such a signal yet. The pulsar timing precision is not quite there, but it is approaching, and the neutron stars that serve as gravitational wave background detectors for NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, are the same millisecond pulsars whose timing data constrains the equation of state. In June of 2023, NanoGrav announced the first evidence for a stochastic gravitational wave background at nanohertz frequencies, likely from a population of supermassive black hole binaries, using 15 years of pulsar timing data. The irony is layered. The objects whose interiors we are trying to understand are simultaneously the instruments we are using to detect gravitational waves from a completely different class of objects. The pulsars are the telescope and the subject at the same time. And the timing data from NanoGrav's pulsar array, the same data used to detect the gravitational wave background, also refines the mass measurements of those pulsars. PSR J161-42230. One of the key two solar mass pulsars is in the NanoGrav array. Its mass measurement has been progressively refined over 15 years of timing. Every improvement in the gravitational wave background analysis is also an improvement in the equation of state constraint. The science is entangled with itself. Let me tell you about something that has been nagging me through this entire investigation. I have read hundreds of pages of papers on neutron star interiors. I have gone through the NICER data releases, the LIGO parameter estimation papers, the chiral effective field theory reviews, the lattice QCD status reports, and there is a sentence that appears in some variation in almost every one of them. The equation of state of cold dense matter remains one of the outstanding open problems in nuclear physics. Or, the composition of neutron star cores is among the most important unanswered questions in astrophysics. Or, determining the nature of matter at supranuclear density is a central goal of multi-messenger astronomy. It appears in the introductions, it appears in the conclusions, it appears in grant proposals and white papers and decadal survey reports. It has appeared for decades, and nobody outside the field seems to notice it. Every popular account of neutron stars tells you what a neutron star is. None of them tell you that we do not actually know. The teaspoon analogy gets recycled endlessly. The lighthouse model of pulsars is explained with beautiful animations. The gravitational wave detection gets its documentary. But the central defining fact that the densest matter we can observe is the matter we understand the least. That fact is never the headline. It is always the fine print. And I want to know why. I think the answer is uncomfortable. I think the answer is that the physics community does not have a good narrative for we do not know. It has narratives for discovery, it has narratives for confirmation, it has narratives for surprise, but it does not have a narrative for a 90-year-old question that remains unanswered despite the most sophisticated instruments and the most brilliant theorists ever assembled. Because that narrative is not triumphant. It is not progressive. It does not end with a Nobel Prize or a press conference. It ends with a shrug and a request for more telescope time. And the public, trained to expect science as a sequence of breakthroughs, does not know what to do with, we measured it more precisely, and we still do not know. So the communicators smooth it over. They tell you what a neutron star is. They skip the part where we do not know what it is made of. And the gap between what the public thinks science knows and what science actually knows grows wider with every breathless documentary that treats neutron stars as a solved problem. They are not a solved problem. They are the problem. I want to take this one step further, because the implications extend beyond neutron stars and into something that touches every branch of fundamental physics. The equation of state of cold, dense matter is not just a question about what lives inside dead stars. It is a question about the strong force itself, about the behavior of quantum chronodynamics in the one regime where it governs the macroscopic structure of objects in the real universe. QCD at high temperature is understood. Lattice calculations work. The quark-gluon plasma at RHIC and the LHC matches theory. QCD at low energy is understood. It produces the proton mass, the neutron mass, the pion mass, all within a few percent through lattice simulations. QCD in the perturbative regime at extremely high momentum transfers is understood to extraordinary precision. The running of the strong coupling constant has been measured at colliders and agrees with the theoretical prediction across energy scales spanning 4 orders of magnitude. But QCD in the cold, dense regime, QCD at finite baryon chemical potential and 0 temperature, QCD in the one place where it determines whether an astrophysical object lives or dies. That version of QCD is the one we cannot solve. And the reason we cannot solve it is not a matter of computational resources or mathematical technique. It is because the theory at a fundamental level, does not give us the tools. The sign problem is not a gap in our methods. It is a feature of the mathematics of quantum field theory at finite density. The partition function is complex. The path integral does not have a probabilistic interpretation. The Monte Carlo methods that have been the backbone of lattice QCD for 4 decades do not apply. Think about that. The standard model of particle physics, the most precisely tested and verified theoretical framework in human history. It predicts the anomalous magnetic moment of the electron to 10 significant figures. It predicted the existence and mass of the Higgs boson decades before its discovery. It accounts for every interaction of every known particle in every accelerator experiment ever conducted. And it cannot tell you what happens to matter when you squeeze it hard enough. The frontier of physics is not where you were told it was. It is not at the Planck scale, 10 to the minus 35 meters, where quantum gravity becomes important. It is not at the energy frontier of the LHC, 14 tera-electron volts. It is at the density scale of a neutron star core, 10 to the 15th grams per cubic centimeter, where the standard model itself admits defeat. And that frontier is not hypothetical. It is not theoretical. It is 12 kilometers below the surface of every neutron star in the galaxy. I want to zoom out for a moment because I think it is possible to miss the shape of what I am describing if you are deep in the numbers. So let me state it plainly. The densest stable matter in the observable universe is the matter at the center of a neutron star, not the densest matter overall. Black hole interiors are denser, but black hole interiors are hidden behind event horizons. You cannot observe them, you cannot measure their properties. You cannot extract information about the state of matter inside them. Heavy ion collisions at RHIC and the LHC produce matter at comparable energy densities, but in a fundamentally different physical regime. Hot and short-lived, lasting 10 to the minus 23 seconds before it cools and hadronizes back into ordinary particles. Everything else in the universe, every planet, every star, every galaxy, every gas cloud, is at least a factor of 10 to the 14 less dense than the core of a neutron star. Neutron star cores are the only natural laboratory for cold, ultra-dense QCD. They are the only place in the universe where the strong force operates at conditions we cannot reproduce, cannot simulate from first principles, and cannot access with any instrument other than telescopes and gravitational wave detectors operating at the limits of human technology. The densest stuff you can actually study is also the stuff you understand the least. And the gap between what we can observe and what we can explain is not closing. It is, with every new measurement, getting more precisely defined, but not narrower. This is not a failure of effort. The people working on this problem are among the best in physics. I have read their papers. I have read the supplementary material. The mathematics is formidable. The statistical methods are state-of-the-art. The observations are heroic. The problem is that the strong force at high density is genuinely, irreducibly hard. It is a strongly coupled quantum field theory in a regime where perturbation theory fails and lattice methods choke. The only reliable anchor points are at low density, where chiral effective field theory works, and at asymptotically high density, where perturbative QCD works. Between those anchors, at the densities that actually matter, that actually exist inside these objects, we are interpolating, guessing, drawing smooth curves between 2 points, and hoping that the true equation of state is among the family of curves we have considered. And the universe is under no obligation to fall within the space of our guesses. I need to tell you about something that happened in 2022 that made this point more sharply than any theoretical argument could. A team led by Sabrina Huth including Peter Pang, Tim Dietrich, and collaborators, published a paper in Nature titled Constraining Neutron Star Matter with Microscopic and Macroscopic Collisions. For the first time, they combined multi-messenger neutron star observations, chiral effective field theory, and data from relativistic heavy ion collisions, specifically from the FOP and ASY-EOS experiments at GSI in Darmstadt, Germany, which collide gold nuclei at lower energies than RHIC to probe the nuclear equation of state at 2 to 3 times saturation density. Their conclusion was that the inclusion of heavy ion data pushes neutron star radii toward larger values. The heavy ion data and the neutron star data are pulling in the same direction on the equation of state, toward moderate stiffness at intermediate densities, but the error bars remain large enough that the central question, what phase of matter provides that stiffness, is still unanswered. The reason I mention this paper is not the specific result, but what it represents. We are now combining gravitational waves from neutron star mergers, X-ray pulse profiles from an instrument bolted to the outside of the International Space Station, nuclear collision data from heavy ion experiments in Germany, and theoretical calculations based on the symmetries of quantum chromodynamics. And even with all of that, the answer to what is inside a neutron star is, we are not sure. That is not a popular science oversimplification. That is the actual state of the field as expressed in its own review papers. And the instrument that was supposed to keep refining the answer may be dying. On May 22nd, 2023, NASA developed a light leak. Sunlight began entering through damaged thermal shields covering its 56 X-ray concentrators. The light contaminated the data. For months, the NASA team worked on a plan to repair an instrument that was never designed to be serviced. Keith Gendreau led the effort. As he put it in a NASA interview, NASA was not designed to be serviced or repaired. It was installed robotically, and we operated remotely. When we decided to investigate the possibility of patching the largest damaged areas on the thermal shields, we had to come up with a method that would use the existing parts of the telescope and station toolkits. On January 16, 2025, astronaut Nick Hague performed a spacewalk and installed repair patches on the damaged thermal shields. By April, NASA was collecting data during more than 70% of ISS daytime. It looked like the crisis had been averted. Then on June 17, 2025, NASA suspended science operations due to a pointing motor anomaly. As of today, its long-term future is uncertain. The instrument that gave us our first precise measurements of neutron star radii may have taken its last data point, and its successor has not been built. But there is something coming. 2 somethings, in fact, and they represent perhaps the only path to resolving the equation of state crisis within our lifetimes. The Einstein telescope is a proposed 3rd-generation gravitational wave detector to be built underground in Europe. Its design is a triangular configuration with 10-kilometer arms cooled to cryogenic temperatures, using a xylophone setup with separate interferometers optimized for low and high frequencies. As of 2026, the site location is expected to be announced, with construction beginning in 2028 and first observations targeted for 2035. The candidate sites are Sardinia in Italy and the Euregio Meuse Rhine region at the border of Belgium, the Netherlands, and Germany. Cosmic Explorer is the American counterpart, a 40-kilometer L-shaped interferometer, roughly 10 times the arm length of current LIGO detectors. The National Science Foundation endorsed it through a March 2025 advisory committee report led by Vicky Calogera at Northwestern, with a preliminary site report due in the fall of 2026, and first light targeted for the early 2030s. Together, the Einstein Telescope and Cosmic Explorer would form a global network roughly 8 times more sensitive than current detectors, with bandwidth extending below 10 Hz. And that extended bandwidth is the key, because what these detectors would be able to do, for the first time, is detect the post-merger gravitational wave signal from a binary neutron-star collision. Let me explain why that matters. When two neutron stars merge, the immediate aftermath, lasting a few tens of milliseconds, is a violently oscillating hypermassive neutron star. It vibrates, it rings, it emits gravitational waves at kilohertz frequencies far above the sensitivity band of current LIGO and Virgo detectors. The spectrum of those oscillations, the frequencies at which the remnant rings, is determined by the equation of state of the matter inside it. And critically, if there is a first-order phase transition in the core, if the matter undergoes a sharp transition from hadronic matter to quark matter at some critical density, that phase transition would leave a specific signature in the post-merger gravitational wave spectrum. A shift in the frequency peaks, a damping feature, something that would distinguish a star with a quark core from a star made entirely of hadronic matter. Current detectors cannot hear this signal. Einstein Telescope and Cosmic Explorer can. Every binary neutron-star merger in the observable universe would be detectable. And from the brightest, closest events, the post-merger oscillation spectrum would be resolved in enough detail to identify or rule out a quark-hadron phase transition. That is the end game. That is what the equation of state crisis is building toward. A measurement, possibly within 15 years, that would tell us whether the cores of neutron stars contain a new phase of matter, a form of matter that vanished from the universe 1 microsecond after the Big Bang and has been hiding inside dead stars ever since, holding them up against gravity's final demand. But we do not have that measurement yet. And until we do, here is what we are left with. We are left with the knowledge that the densest observable matter in the universe is the matter we understand the least. That the strongest force in nature, the force that holds every atom in your body together, refuses to yield its secrets at the one density scale where the stakes are highest. That the difference between a neutron star and a black hole, between the densest thing you can study and the densest thing you can never study, is determined by physics we cannot calculate. That there are objects in our own galaxy right now spinning at 700 rotations per second, held together by something that may be a state of matter that has not existed freely since the universe was a microsecond old. And we cannot confirm this. We cannot deny it. We can only measure the shadow it casts on the space-time around it and try to work backward. Let me close the loop on Jocelyn Bell Burnell, because her story has one more chapter that connects to everything we have discussed, and I promised that the biographical threads would return. In 2021, Jocelyn Bell Burnell received the Copley Medal from the Royal Society, the oldest and most prestigious scientific award in the world, dating to 1731. She became only the second woman ever to receive it, after Dorothy Hodgkin in 1976, 54 years between them. The citation honored her discovery of pulsars and her subsequent lifetime of contributions to astrophysics. But here is what I keep thinking about. Bell Burnell discovered the objects whose interiors we cannot explain. She found the first evidence that neutron stars are real, observable things that can be studied and measured and weighed. She handed the community a window into the most extreme matter in the universe, and the community thanked her by giving the Nobel to someone else, and then spent 50 years looking through the window and arriving at the conclusion that they do not understand what they are seeing. That is not a criticism of the community. The problem is genuinely hard, but there is something about the arc of it. From a 24-year-old woman noticing a quarter-inch of scruff on chart paper to a 90-year crisis in nuclear physics, that feels like it should be a larger part of the public consciousness than it is. The signal she found is still pulsing. The questions it opened are still unanswered. I also want to return to the fact that NICER, the instrument that was supposed to resolve the equation of state question, may be dying. Because that detail is not incidental, it is diagnostic. Here is an instrument that was conceived, designed, built, launched, mounted on the outside of the International Space Station, operated for 8 years, damaged by sunlight penetrating its thermal shields, repaired through a spacewalk that was never supposed to be possible, brought back to partial functionality, and then knocked offline again by a motor problem. Its replacement has not been funded. Its data pipeline is still being mined, and the papers it has produced, the radius measurements of JG00, J0740, and J0437 represent the best measurements of neutron star structure that humanity has ever made. They are also, possibly, the best measurements we will make for a decade. The Einstein telescope and Cosmic Explorer will probe the equation of state from the gravitational wave side, but from the X-ray side, from the pulse profile modeling side, NICER may be the end of the line for the foreseeable future. The X-ray instruments proposed for the next generation, like the Enhanced X-ray Timing and Polarimetry Mission, XXTP, led by China and European partners, are still in development and not expected to launch before the early 2030s. There may be a gap, a window of years where no new X-ray mass radius measurements arrive, where the community is left to reanalyze existing NICER data and wait. The equation of state crisis is not going to be resolved quickly. It is not going to be resolved by a single measurement. It is going to be resolved, if it is resolved at all, by the slow accumulation of multi-messenger data over decades, combined with theoretical advances that do not yet exist, using instruments that have not yet been built. The timeline is generational. And in the meantime, the stars keep spinning. The matter in their cores keeps refusing to identify itself. The densest stuff in the universe keeps being the thing we understand the least. And the equations, Oppenheimer's equations, the equations that describe how a self-gravitating fluid balances itself against collapse, sit there with a blank where the answer should be. A blank labeled equation of state. A blank that has been blank for 87 years. 1 billion neutron stars in the Milky Way. Each 112 kilometers across. Each one containing matter at 5 to 10 times nuclear saturation density. Each one holding itself together with a mechanism that the most successful theory of the strong force cannot predict. 1 billion objects, each one a locked box. Each one containing something we recognize from the first microsecond of the universe. Something that vanished as creation cooled and thinned. Something that found a way to persist, to survive, to hide in the compressed hearts of dead stars, where the density was high enough and the temperature was low enough for it to endure. And we put a washing machine-sized X-ray telescope on a space station and tried to open the box. And what we found inside does not fit any model we have built. The data is precise. The theory is incomplete. The densest observable matter in the universe is the least understood substance in physics. It is sitting there, right now, in the cores of objects we can see, obeying laws we wrote down, and refusing to tell us what it is. There is something humbling about that. And something else too. Something that I think sits closer to dread than to humility. Because the equation of state crisis is not just about neutron stars. It is about the limits of human knowledge as they actually exist right now in the 21st century. We have a theory of the strong force, quantum chromodynamics. It is among the most precisely tested theories in all of physics. It predicts the results of particle collider experiments to extraordinary accuracy. It correctly accounts for the masses of protons and neutrons to within a few percent using lattice QCD. It is, by any reasonable standard, one of the great achievements of human reason, and it cannot answer the simplest question about the interior of a neutron star. Not because it is wrong, but because the mathematical techniques required to apply it at the relevant conditions do not exist. The theory is correct and simultaneously useless. The equations are there, the answers are not. I keep coming back to something Oppenheimer and Volkoff wrote in their 1939 paper. After deriving their maximum mass of 0.7 solar masses for a free neutron gas, they noted, almost as an aside, that the effect of repulsive forces at small distances would tend to prevent the collapse. They knew their model was incomplete. They knew the nuclear force would change the answer. But they could not calculate how, because the nuclear force at high density was not understood in 1939. It is not understood in 2026. The tools are better. The measurements are better. The theoretical frameworks are more sophisticated. But the fundamental problem, the problem of what the strong force does to matter when you compress it to 5 or 10 times the density of an atomic nucleus, is the same problem Oppenheimer and Volkoff identified 87 years ago. They left it for us, and we are leaving it for the next generation, for the generation that will build the Einstein telescope and cosmic explorer, that will listen to the death rattle of merging neutron stars in kilohertz gravitational waves, that will either hear the signature of a quark-hadron phase transition or hear its absence. Zwicky predicted neutron stars in 1934. Bell found them in 1967. 33 years. The Tolman-Oppenheimer-Volkoff equation was written in 1939. The Hyperon puzzle emerged in the 1980s. NICER flew in 2017. The Anala evidence for quark matter was published in 2020. Einstein telescope might take data in 2035. The timeline for this, one question, what holds up a neutron star, now spans over a century of physics. And at the center of that question, at the center of the object it is about, in the innermost few kilometers of a sphere smaller than a city, there is matter. Cold, dense, stable, possibly free quarks locked in a color superconducting condensate, possibly neutrons crushed so tightly that the three-body force between them becomes the dominant feature of reality. Possibly something we have not yet imagined, something that existed for 1 microsecond 13.8 billion years ago, and then vanished as the universe expanded and cooled and diluted itself into the thin, ordinary world we live in. Except it did not entirely vanish. It hid in the crushed hearts of dead stars, in objects so dense that a teaspoon of their substance outweighs a mountain, in objects so compact that their gravity bends light around their own surfaces, in objects spinning so fast that their equators approach the speed of light, in objects that we have measured with exquisite precision and still cannot explain. The densest observable matter in the universe, the least understood substance in physics, sitting 12 kilometers below a surface we have mapped with X-rays, emitting gravitational waves we have detected, obeying laws we wrote down 100 years ago, and refusing to tell us what it is.